Welcome to part 3 of problem solving with abstractions. In the first part, we ended up getting stuck with implementing a new feature in our code, but in the second part, we learned a lot about levels of abstraction, how using too many at once could be scary, unsettling, or disquieting, and that artists, divers, and programmers all strive to keep things at a single level of abstraction. So in this episode, we'll take that to heart, and combined with the lessons from part 1, perhaps we can finally solve the problem. We have found that this code is on several different levels of abstraction. And of course, we want to keep those levels, but isolate them in functions of their own, making sure that each function is only a single level of abstraction. So let's get to it.
First of all, it doesn't really help that our abstract functions from last time are right here in the middle of the function. The whole idea of abstraction is that we don't have to look at all the details all the time. So let's move them out of the function, out of sight. Down here they go. Now we can see the entire function. And it is a bit of a mess, so let's begin cleaning it up. First, the delta calculation. It is something technical, very close to the platform and not really part of the problem domain that the user understands. So it'll never fit in with the rest of the abstractions. And you could argue that we should leave it as is, as something that doesn't belong, so it has to be on a different level of abstraction. But we don't really want or even need to draw attention to it, so we'll treat it the same as every time else and abstract all of it into a function. Most editors have built-in tools for doing these kind of changes where we move code around without changing what it does. It is called refactoring, and the specific operation we want to perform is extract to function. And the reason it's called extract and not abstract is that we could use it to simply move code around without making it more abstract. We just take it out of one function and put it into another. But let's extract this and it's done, but it shouldn't be called new function. We use it to calculate delta, so that's what it should be called, calculate delta. Our move functions here, they can be left as they are, but this for loop, last time I didn't want to put it into a function, but it really should, so let's abstract that as well. And it checks collisions between the asteroids and the spaceship. So in a sense, it ought to be called that. Check collisions between asteroids and spaceship. But that's a bit of a mouthful, so let's settle for check collisions. Then there is this visual spaceship thing here. It does something with the visual spaceship, translates it to the x and y of the spaceship coordinates. I think it displays the spaceship at the correct position. So let's extract all of that to a function called display spaceship. And this loop, it does something similar, but for the asteroids. We could either create a function for the inner code, this part here, and call it display asteroid, but we already have a move asteroids function. So let's just take the entire loop and extract it to display asteroids. And then these two lines here at the bottom, well, they also seem to display something. This one displays the score or the points. Wonder what the difference is, but let's just rename it, extract to a function. And let's call that display score. And the last one, that displays the health.
It looks much nicer now, doesn't it? I mean, even if you hadn't just learned about single level of abstraction and how mixing different levels could be unnecessarily confusing, you can almost feel the calm in this function, how every single line is expressed as something someone close to the surface would understand. First we move the spaceship, then the asteroids, and then the shots. After that we check for collisions, and then we display the spaceship and the asteroids, probably at the new position they were moved to, and finally we display the score and the health. This is something that even the user, the player of the game, would agree with. Yes, that is what is happening. And it also makes it obvious what went wrong earlier, why our code didn't work as expected. See, we had create asteroids and create shot, or fire shot as we called it, and move asteroids as well as move shots. But now there's also display asteroids, but we're missing display shots. So there truly is value in making the inside of a function stay on a single level of abstraction. Now we understand everything that goes on at that level and where we need to dive deeper, which sub-cave to swim into, so to speak. So let's do that now and create the missing display shots function.
First, we make sure that we actually call it, even though it doesn't exist yet. Display shots. And then we go to display asteroids and copy it in its entirety. Put it up here and remember to rename it to shots and loop through the list of shots, and everything inside it is a shot. Notice how we still have more than one level inside the function. First is the loop that goes through our list of shots. That's a fairly high level. Then for each of those objects, we do something to the visual shot. That's part of the platform and thus a very low level. But in that low level, we mix some of the higher level properties of the shot together with some code we might not understand. So we have this foreground background thing going on. We can choose to ignore the platform dependent code and focus on our shots, or we can ignore the shot and only focus on the platform code. For now, we can probably ignore all of it, so let's swim up again all the way to the surface and check if it works. It does. It does go a bit slow and sometimes seem to fire more than one shot, and they shouldn't really be on top of the spaceship. And they're also a bit too far to one side. But that's details. We can fix those later. Let's just celebrate that it works and continue implementing the missing features, meaning that we have to dive deeper into this function here, remove shot.
What does it mean to remove a shot? There isn't anything else in the program that gets removed, so we don't have any other abstraction higher or lower that we could take inspiration from, let alone copy. So we are a bit on our own, and we have to analyze the problem of the abstract idea of removing a shot and figure out the concrete implementation that will result in that happening. And that means that we have to understand all the levels between the surface where the user can see the visual shot and the platform where it exists as some sort of object. Shouldn't be that hard work, but still a bit of a challenge. Would be nice to at least get a hint, maybe from our senior programmer. Guess he's not available. Probably in a meeting. But now that I think about it, remember how we imagined the shots being the same as the asteroids, only turned upside down? And isn't removing a shot the same as creating a shot, only the other way around? Shouldn't remove shot simply do the opposite of create shot, fire shot. Maybe if we dive into that function, we'll understand what needs to be done.
Let's see. First, it creates a div. That is something very close to the platform. And then it adds a class to that div and it inserts it somewhere in the document, meaning displaying on the screen. After that, it creates a shot object with all of these properties here, where we at least understood X and Y, and visual turns out to be the link to the div. Okay, and then that object is pushed to the list of shots. Okay, I clearly see two different things going on here at two different levels of abstraction, the platform and our shot object. So in order to make this entire function a single level of abstraction, we need to extract the code into two separate functions. These three lines, they create the visual part of the shot and adds it to the screen. So let's extract them into a function called add shot to screen, for lack of a better name. And then the rest, they create the data object and add it to the list. So extract that to add shot to list. And it even receives the div we just created, so it can be stored as visual. Cool.
Now the fireshot function is very clearly telling us that it does two things. It adds a visual shot to the screen and then adds a shot object to the list of shots. That means that remove shot should do the opposite. Call remove shot from screen to remove the visual shot, and then call remove shot from list to remove the shot object. Okay, easy. Let's code that.
Get rid of the not implemented and instead call the two still non-existing functions. Remove shot from screen, receive the shot, and remove shot from list. And both of them should receive the shot so they know which shot is to be removed. Then we create these two functions and make them say not implemented. Function remove shot from list from screen, like this.
Now you might immediately argue that we aren't any closer to solving the problem. In fact, we now have two not implemented functions, so you could say that we are twice as far from a solution. But we have moved to a lower level of abstraction, and since there's always more details on the lower levels, after all, abstracting is about removing or ignoring those details, it makes sense that there are also more details to implement. So I wouldn't worry at all, but just dive into the functions one at a time.
Remove shot from screen should be the opposite of add shot to screen. And as we discovered earlier, that created a div element and added it to the screen. So we need to remove a div element from the screen. That sounds very close to the platform, which is great because that means that if we don't know how to do it, someone else does, and we can simply search for the answer. So just say remove div, and turns out there is a remove method that we can use if we have the element, and we do. That was stored as the visual property in our shot object. So remove shot from screen should simply be shot.visual.remove. Nice and simple. Now for the remove shot from list, that is the opposite of add shot to list, that created an object and pushed it to a list. That is also an abstraction very close to the platform, the JavaScript programming language. So let's search for how we remove something from a list. JavaScript remove item from list. And I'll skip the AI answer and go straight for Stack Overflow. And here it says, find the index of the array element you want to remove using index of, and then remove that index with splice. Okay, and here's an example. We have an array, and then we find the index of the element called 5, and for us that would be shot. And then there's an if statement for safety, but we ignore that. And then we just splice the array with the index and the number 1. Okay, so let's try that. Remove shot from list. We find the index is the shots index of shot, and then we splice shots with that index and the number 1. Cool, let's try it. I fire some shots, and when they reach the top, they disappear, I think. Let's see. They are no longer on the screen, and they are no longer in the list. Very, very cool. Now, we only need one last thing, the entire reason for everything we've done so far, checking if those shots collide with the asteroids.
It is a bit disheartening that we've now spent more than an hour working on this feature, and so far we've only solved the smaller sub-problems of firing shots and making them move up the screen. We haven't even looked at the main problem, making it possible to actually destroy the asteroids. There is this joke in software development that the first 90% of the code takes the first 90% of the time, and the remaining 10% takes another 90%. This is both a joke about every software project being delayed, taking almost twice as long as initially expected, and about programmers being overly optimistic, always thinking that they are nearly done. When they know the solution to a problem, they tend to see the entire ocean with every level of abstraction and know exactly what to do and how long it will take. But when they don't know the solution, they only see the abstract surface and forget that there might be an entire unexplored ocean below. Thus, the well-known bits, the easy part, looks huge, but the hard part seems small in comparison. And as the project progresses, it turns out to be the other way around. But for us, it turned out that the initial simple stuff, making the shots move on the screen, took much more work than anticipated. So can we expect the last part, actually checking for collisions between shots and asteroids, to take even longer? Have we done 10, 30 or 90% of the work? Well, I like to think that we have done a lot of preparatory work that will make the job easier. Like when painting a room, all the annoyingly time-consuming work with covering up panels, doors, windows, etc. If you don't do a proper job with the preparation, you end up with splotches of paint in all the wrong places. But when done properly, the actual painting is extremely easy and takes hardly any time at all. My hope is that all the work we have done using correct abstractions and making sure that everything inside each function is at the same single level of abstraction, that all that work is the annoying prep work, and that it will help us make solving the problem much, much easier. Because when you think about it, most of the work we have done has been about improving the abstractions of the original code. Every time we hit a bump in the road, it was because we needed more abstractions, and it sometimes took a bit of work to figure out how. But the actual features we implemented took almost no time. So Let's see if it has done the same for our final part here, checking if shots collide with asteroids.
It's going to be inside our check collisions function, so let's dive into that. That loops through all the asteroids, and for each one, check if it is colliding with the spaceship. That's fine as it is, so let's keep that and add some more. In addition to checking for collisions with the spaceship, we also want to check for a collision with a shot. So if is colliding the asteroid with a shot, but there's more than one shot, so we need to loop through the list of shots, and for each one check if that one collides. So we write for const shot of shots and move the if statement inside the for loop, and if they are colliding, then what?
Then they are both destroyed.
Oh yeah, that's right. We should remove both of them. The shot, since it has been spent, and we should also remove the asteroid, because it dies. Remove shot we already have from before, but remove asteroid does not exist yet. But remember how we copied everything else from asteroid to shot? Surely we can do the same again, just the other way around. So let's copy remove shot and all of its related functions down here to remove asteroid. So now just change shot to asteroid, and when you have to edit a lot of different places at the same time, like this shot and this shot and this shot, the easy thing is to use multiple cursors. You simply click the first one and then hold down Alt or Option or whatever the key is for your editor, and click the next one and the next and the next and the next, and then you mark the shot and write asteroid like this. And for the inside of the functions, this shot is now an asteroid, and the same as this, and the same as this. And I just need to remember to also change shots and not rename it this time, but just change it from shots to asteroid. And this one. So now we have remove asteroid from screen, remove asteroid from list. Let's try it out. And it works.
Whoa, that took like no time at all. So it truly did help. All that annoying prep work did manage to make the actual solving of the problem extremely easy. By making all of these abstractions, we created some building blocks that we could reuse later. And by keeping the inside of functions at a single level of abstraction, we made it much, much easier to copy from one abstraction to another. It has been a bit of a trip though, like diving in a very complex cave system. So let me try to recap it into something like a guideline, a step-by-step list of how to solve problems with abstractions. We always begin at the surface and try to understand the problem from the user's point of view. We do think like a programmer and try to break the problem into as small bits as we can, but we stay at this high level of abstraction using the same words as the user would. We do not dive into the water, into the code yet. When we do dive into the code, we don't go too deep. We continue to use the same abstractions. We create variables and functions with names that the user would recognize. And at first, we don't worry too much about what is supposed to be inside the functions. We just create them and make them say not implemented. Then we dive further down and actually implement the functions, gradually go to lower and lower levels of abstractions until we hit the bottom, the platform. Because even when we don't know how to do something, we can probably express it a bit less abstract. And when we do hit the bottom, we can easily search or ask for a solution that works for anyone using the same platform and doesn't care one bit about our many levels of abstractions above. If we're lucky, we can swim all the way from the surface down through the abstractions all the way to the platform and implement everything as we go along. Usually we're not that lucky though. Not that programmers are particularly unlucky, it's just that there's always something unexpected, some detail that we couldn't foresee when we were at the surface. If you're new to programming, this might frustrate you, but as you gain experience, you'll realize that there's nothing that can be done to prevent it, and that a big part of being a programmer is dealing with unexpected problems. One thing we can do, though, is to look for solutions already in the code. If we can find another abstraction, not on another level, but another thing on the same level, where a similar problem has already been solved, then maybe we can copy that solution. To find that thing, we first have to abstract our thing with a problem to a higher level of abstraction, like the vet abstracted Bessie to a cow to compare her with other cows secured of similar diseases. Sometimes we do have to go above the surface to find some truly abstract, fluffy concept that the things have in common. But when we succeed, we don't simply copy memories or experiences, we can literally copy the code from one thing to another. If we don't find anything to copy directly, but we do find something that does the exact opposite of what we want, then we might be able to turn the code upside down and write new code that does the opposite of the opposite. It can be as simple as moving up instead of down, or more complex like removing instead of creating. And it really helps if the functions we are copying or turning limit themselves to a single level of abstraction and use additional functions for the lower level details. It's easier to imagine the opposite of the abstract add shot to screen than the platform-specific document query selector insert adjacent something. And if you aren't sure if you're using more than a single level of abstraction, just look at the code. Does something seem a bit off, or does part of it not fit in? Then abstract that part into a function. It doesn't have to be an exact science. So this is the guide. It sure looks simple enough. Just remember that you will have to swim up and down a lot. It is hardly ever going to be a straight line from surface to bottom. You will probably have to retrace your steps, maybe revisit the same code over and over. And often you can't finish solving one problem before you solve another, and that then requires yet a third problem to be solved first, and they just keep stacking up. It's hardly ever going to be a smooth ride all the way down. But that's all part of the fun. You get to know this cave system that the collection of functions create. And by refactoring them into better abstractions as you go along, you make the ride much smoother for the next visitor. Who knows, it might be your own future self. You can download this guide from a link in the description if you want a copy, but you might not need it. As said, it isn't an exact science, just some abstract ideas. Maybe you feel like it was all a bit too easy. Like everything turned out all right. If not right away, then at least as soon as we had abstracted it a bit more. Almost like it was planned in advance. Well, I did actually cut a few mistakes from the video, but otherwise you're right. It was a surprisingly smooth ride, even with all the ups and downs through levels of abstractions. I mean, apart from wrapping some of the original code in better named functions, we hardly had to change any of it. And if we don't fire any shots, the code that the computer runs is exactly the same as before. Because as it turns out, our senior programmer did actually use abstractions when he wrote the original code. He even suggested as much when we asked him about the collisions.
And they can all be interpreted as circles, with the
He had abstracted the spaceship and the asteroids all the way to circles, a truly abstract concept. I mean, there is no such thing as a circle in real life. It only exists as a mathematical model, an idea of a perfect round thing. But when abstracting to circles, you can use Pythagoras to check if they intersect or overlap. And that is how he probably originally solved the problem of checking if the spaceship and the asteroid collide. He abstracted way above the surface. He just didn't tell anyone about it, or his code certainly didn't. So he might have been thinking in abstractions more than using them. He wasn't doing abstractions in a way that we were able to see. We kind of did the same when we abstracted asteroids and shots to things that fly around in space. We thought about them in that way and it helped us solve the problem, but we never wrote anything about it in the code. All the other abstractions we did use all the time though. We wrote functions called add shot to screen and add shot to list and so on. Come to think of it, that part was actually fairly easy to abstract. All we had to do was cut the code to create a single asteroid out of the loop that made several. And in that cut code, the first couple of lines created the visual part and added it to the screen, and the rest created the object and added that to the list. So our senior programmer probably was thinking on the same high level of abstraction as us, but he only wrote code on the lowest possible level. In a sense, he was like Picasso before Cubism. Remember how he claimed that all art is an interpretation, or actually two. First, the artist interprets what they see in the real world and puts it into the painting, and then we interpret what we see in the painting. And all artists, no matter how realistic or abstract the art, interprets the world as geometric shapes and patterns of light. If you've ever taken a drawing class, you no doubt learned to draw the human body as a collection of cylinders, boxes, and spheres. Though usually you hide them or limit them to your sketches or simply keep them in your mind. But Picasso chose to highlight those in his Cubist works, to draw attention to the exact interpretation that he was making while painting. He was doing abstraction. And you should do the same. Let the code show your abstractions. Be like Picasso and let the code explain how it should be interpreted. Make the viewer know what you were thinking when you wrote it. Don't limit yourself to only think in abstractions, only use them at the lowest levels, like our senior programmer. Use all the levels, at least all the way between the platform and the surface. Flying too high might end up hurting you. But try it. Use them. Let them solve problems for you. Let your code speak for you. That was problem solving with abstractions. At least all I had to say about it. I hope that you learned something useful, that it has been the optimal blend of theory and practice, of abstract and concrete, and that you have been able to focus on some things and ignore others. There is, of course, a lot more to abstractions that I haven't even touched upon. When we find a higher level of abstraction that is shared by several things in our program, like our thing that flies in space, that is called a generalization. And generalization is another huge topic in programming that I'll definitely make a video about at some point. And then there's also the somewhat opposite separation of concerns about how you should separate parts of the code that doesn't abstract to anywhere near the same thing, like we did with the visual shot and the shot object. That is also a huge topic for another future video. And then, of course, there's the whole world of object-oriented programming that introduces a rather wonderful idea of abstraction, where each object, in our case spaceship, asteroid, and shot, deal directly with each other on a very high level of abstraction, more or less hiding all the lower levels of code. And speaking of hiding, I have been careful to always talk about levels of abstraction, but there is also this thing called layers of abstraction, where you deliberately write your code so that it isolates the different levels of abstraction so other programmers can't, or at least shouldn't, swim any further up or down. They are trapped at a certain depth in a layer. That is a huge topic in larger systems, but also in the way we use modern programming languages and the many advanced platforms we have. It does solve some problems, but of course it also comes with its own possibilities for new problems and misunderstandings. In fact, so does object-oriented programming, especially when working with the somewhat controversial idea of inheritance and abstract objects. It can sometimes cause more problems than it apparently solves, and has demonstrated that using too many abstractions can make the code harder to understand, quite the opposite of what we want. The same can happen when we rely too much on single level of abstraction, because we end up with so many functions that we create a complex of caves where you actually do get lost. And don't even get me started on the problems that occur when you go too far above the surface. But I wanted this video to be purely positive and demonstrate all the good that abstractions can do for us. And of course, like any good thing, it can be overdone or misused. I will have to make another video about problem creation with abstractions, which of course won't be a guide like this one, more like a collection of warnings and discussions of what not to do. But you don't need to know any of that now. There's still a lot to do in the game. The rest of the code, the parts we haven't visited yet, could probably also benefit from being refactored into single levels of abstraction. And then there's all the details with the shots being too slow, too far to one side, and so on. And the collisions could probably also be a bit tighter. I think you should try to do some of that now. And since you know how to use abstractions to solve problems, it should be easy for you to solve those on your own. Maybe you can even add more features, like scoring points or collecting health boosts. I've put my own work in an accompanying video, together with all the code work done so far. There isn't going to be any new information in it, so you don't have to watch it, but if you want to, there's a link up here and in the description. At some point in the future, I will make the video about creating problems with abstractions. When I have, there will be a link to it here. And also, at some point, there will be a link to a video about layers of abstraction here. But for now, take a break from watching videos and go ahead and solve problems in projects. Preferably your own, but you can take a copy of mine for some practice. It should be easy. After all, we are 90% done.